Hey there, in this video we're looking at C++ Interlude 2 in the Walls and Mirrors Data Structures text. And this interlude is on the subject of pointers and polymorphism and memory allocation. Now, pointers are super important in C++ programming, really any programming, although sometimes it might be hidden from you. And two primary things that we need to use pointers for: number one, polymorphism. And that's where we ended at the end of Interlude 1, when we'd set up a class hierarchy, we'd redefine some functions, and we need some way for the program to pick which version of the redefined functions to use, that you really need pointers to make happen. Number two, dynamic memory allocation. When you need to access the majority of available memory in your computing system in C++, you need a pointer to access that kind of memory. So several important things. Again, this should be mostly a review from your prior course, but we want to make sure that we're very clear-headed about the resources we have available to make this stuff happen. Okay, item number one, let's review the memory layout of what a slice of memory normally looks like when you have any program running on a system. So you have memory. And what you have is, for any particular program, you get a fairly small slice, traditionally at the top of the memory system. It's called the runtime stack. And on our systems nowadays, your program might get like 1 megabyte, 2 megabytes. It's not very much. And that's where you're going to put all of the information about individual function calls. So you call a function, and all the arguments coming into the function get stored there, the local variables, the address where you need to return to later on, all that gets saved up there in the runtime stack. Now, the majority of the memory in the system, this big middle part here, is unallocated, undedicated to any particular program. And that only gets used when a program asks the operating system, I need more memory, and then you start using that section up. Now, most people call that the heap memory, or in this picture, the application heap. Now, there's a little bit of an awkwardness, is that completely separately, there's a particular data structure that we can study later called the heap type data structure. And that's in our Walls and Mirrors textbook, chapter 17, if I recall correctly. So in order to not get confused between the memory called the heap and the data structure called the heap that are totally different, our textbook here is instead going to call that the free store, just to have two different terms for that. So normally I think of that as the heap memory, but we're going to call that the free store here. Now, down traditionally at the bottom of the memory system, you have a slice of static storage. That's where global constants would be sitting, where string literals would be saved there, things like that. And then right at the bottom of the memory system is where you'd actually have the code, the compiled machine code that's running your program. And of course, the CPU is just grabbing one line at a time, bringing it to the CPU, decoding it, executing it, and then incrementing down to the next line past that. So normally that's what's happening there. The things that we as C++ programmers kind of directly interact with are the stack at the top, and I'm going to have to practice calling this the free store of that larger supply of memory in the middle. Okay, so like we said there, a little bit of review there, local variables inside a function get stored in the stack. So you come into a new function call, and all of that function's local variables, the incoming parameters get stored there, the address of where to go back when the function wraps up, all that stuff is being put in what's in a block of memory. It's not very big, called the activation record, is what this book calls it. I'm used to calling that a stack frame. So one little package of everything you need for one function stored in the stack memory. And then when the function wraps up and you get out, that stack frame, that activation record, is, I'll say, marked for elimination, marked for recycling so that somebody else can use it. And you might as well just assume that it's been destroyed. So it's probably gone after you get out of the function, and you can't rely on that stuff being there anymore. So temporarily put on the stack, function wraps up, it gets cleared out. That's how the stack works. Now, the other thing is when you need more memory, now you start having to deal with dynamic memory allocation. When you're allocating, you're requesting new memory within C++, the operator new, the keyword new. Exact same thing in Java for what it's worth. So when you use the new operator, it goes to the free store, it finds a block of memory big enough that you need, allocates it to your program, and then returns the address of where it found it that you need to store in a pointer variable in order to keep track of where it is. So the new operator, like it says here, returns the memory address of where it found your new block of memory. It's your responsibility as the programmer to store this in a pointer variable so you can find it. And then that kind of object in the free store persists between function calls. So whereas local variables just get recycled at the end of the function, that's not the case for memory in the free store. It's going to stay there between multiple function calls until you specifically ask to clean it up in your code. So it works very, very differently. And this is what you need to do when you are working with larger data structures. Okay, so here is a little picture kind of to clarify what happens when you are doing dynamic memory. And what you have here is you're declaring a new object. Remember our last interlude, we had this hierarchy of 3 different types of boxes in a video game: plain box, toy box, and magic box. And they're templated so they can store any kind of thing inside them. So what you have here is you have a line of code where they're declaring a magic box storing a string. Remember what the asterisk is, pointer. Okay, so a pointer to where you can have a magic box that stores strings. They're going to call this the myBox pointer, which makes sense. And they're going to set it, they're going to assign it the result of a call to a new magic box storing a string. So there's the new operator. It's going to go to the free store, find space for a magic box that can store a string, return the address, and that's what you're saving in myBox pointer. There's a second line of code here called where you're declaring a standard string. That's the type. You're going to call it SomeItem, and you're just setting that to the string literal something. So at this point, right, and then having done that, you can use the myBox pointer. There's that arrow notation to access one of the member functions by an object pointer, which you're going to be seeing a lot more of in this course. So from the myBox pointer, you're calling the setItem function. You're passing in this SomeItem, that's the string holding something. And remember that setItem normally just copies that into the internal memory of that object. So at this point, on the runtime stack, you've stored these things that you've declared locally. So you have the SomeItem string is in the stack as a local variable, and also the myBox pointer is in the stack for this activation record, the stack frame for this particular function that you're in. In addition to that, because of the new operator over in the free store, you have declared an actual myBox object, and you actually have passed in a copy of the something string because of that third line of code there. And the address of that, that's what's actually being stored in myBox pointer. Our system, we're probably using a 4-byte pointer. It's not taking up very much space and telling us the address about where is the magic box object sitting over in the free store. So you get a couple things in the stack. That's the local variables. And then the thing that we called new for, that's sitting in the free store. When this function wraps up, that activation record just gets scrubbed out of the system, but the magic box will still be sitting in the free store. Okay, so kind of focused on that, and this is how we normally depict a pointer and the object that it's pointing to in a picture. We're going to stop indicating. Remember, the pointer is over as a local variable in your function, and the object is sitting in the free store, but we're just indicating this is a pointer and it's telling us where this object actually is in the memory system. You're probably used to seeing those kinds of pictures before, I assume. All right, now remember, the object sits around in the free store effectively permanently until you specifically tell the system to recycle it. When the memory is no longer needed, then you deallocate it with the keyword in C++, delete. You say delete the thing at this address, the thing at this pointer, and the operating system goes, okay, I get it. You don't need it anymore. I'm going to mark this as being available for use by other programs now, and you don't own this piece of memory anymore. Now, assuming that the pointer is a class member. If it's a local variable, then the second bullet point doesn't apply. You're probably going to have a function, get an object, do whatever, the function ends, don't worry about this. But if the pointer variable persists, if it's a class data member that's going to be in your object for a while, then the recommendation is after you delete the thing, set the pointer to null pointer, and that's going to be the signal that that pointer isn't linking to any actual object anymore. And then later on, you can like have an if statement. If it's null pointer, okay, I don't have anything, maybe let's make a new thing. But if it's not null pointer, don't override that address because you'd lose access to the object in the free store. And that problem, that mistake that might happen is called having a dangling pointer. So if you forget to do that, you have a pointer it has an address, but it's pointing to someplace where you've recycled and scrubbed the object away. It's not actually pointing at a legitimate object. And as it's pointing out here, dangling pointers that we did talk about in our prior semester course is a source of very serious errors, very much like what I'd refer to as a buffer overflow when you're working with arrays. If you try to call a function in a place that doesn't have an actual valid object, literally anything could happen. Maybe it's fine. You might accidentally have it work, which is actually really terrible because it's going to trick you into thinking your program's okay. It could corrupt other memory. It could overwrite other programs. That provides an opportunity for hacking vulnerabilities where people can take advantage and take control of your system. All kinds of really terrible things. Very difficult to debug. If crazy, unpredictable things start happening sometimes and you don't know what it is, I start to think about that might be a buffer overflow, that might be a dangling pointer accessing invalid memory. And I got to tell you, that is a very hard job to fix. So really, really try to avoid that. Okay, so we'll talk about this. We'll talk about avoiding memory leaks a little bit because it's one of, if not the single biggest problem with low-level C++ programming. So everything we can possibly do to avoid this terrible, terrible error, we're going to try to do. So a memory leak occurs among the problems you can have with pointers. A memory leak occurs when an object has been created and stored in the free store, but the program no longer has any way to access it because you've lost the pointer to it. So here's a very short example of a little function that causes a memory leak. It's called myLeakyFunction. So you pass in, remember again those three types of boxes, plain box, toy box, and magic box. You pass in some kind of item that you want to store in a box. Okay. So here we're going to dynamically allocate a new toy box. You make a toy box of a double pointer called SumBoxPointer. Okay. You call for a new toy box that can store a double. Great. And the operating system does that, finds it on what I would call the heap, sends you back the address. You store it in the SumBoxPointer. You do something with it. You call this, using SumBoxPointer, you call that object site item. Great. And then the function ends. Okay. Well, that's what a lot of functions look like. But the problem is that the SumBoxPointer was a local variable on the stack. When you get out of this function, that stack frame gets wiped out, and now you've lost the pointer. So the new toy box is sitting in the free store, and you've lost any way to be able to find it because you just wiped out the pointer as a local variable in this function. And from now on, that toy box is going to be sitting in the free store permanently, and there'll be a little slice of memory that nobody else can use. And back in the day, Actually, that would be a wasted piece of memory that you could only get back by rebooting your system. Nowadays, Windows is smart enough that I think it will at least figure that out when your program ends. And it will detect that, well, this program doesn't even exist anymore. And then Windows will be able to recycle it and use that memory for other programs. But as long as your program's running, there's a chunk of memory there that's totally not doing any good whatsoever. So that's what a memory leak might look like. And here's a second example of how you might possibly make a memory leak. So in this example, we have 3 lines of code. And the first code is making a magic box pointer, a magic box to store a string specifically, pointer, called myBoxPointer. And we're setting that to the result of a call to the new operator to make a newly dynamically allocated magic box. So what that does is it makes a magic box object on the free store and then stores the address of that in your myBoxPointer. So myBoxPointer is telling you where to find this object on the free store. And we basically do that again. So another magic box pointer called yourBoxPointer, allocating another new magic box. So you get this second object that's in kind of light blue there, and yourBoxPointer is tracking where that is in the free store. And then there's this third line of code. It's just an assignment statement. Remember, these are pointers. So it's taking the address that's in myBoxPointer and copying it into yourBoxPointer. And the problem there is you just overwrote what used to be in yourBoxPointer. So now you have both myBoxPointer and yourBoxPointer directing you to where that first magic box object is. And there's a lot of reasons why you need that. Like different parts of the code might need to access a particular object in different contexts. I mean, you might need multiple pointers to do that. But again, the problem is you just overwrote what's in yourBoxPointer. And so remember that second object, that second light blue object is still sitting permanently on the free store. And now you have no way to access it, and you have no way to tell the system to recycle it with a delete statement. So again, a chunk of memory that's lost, that's totally unusable to any program in the entire system until your program finally ends and the operating system figures to clean up all this stuff. So it can be as simple as an assignment statement. The wrong assignment statement, that's all it takes. Overwrite the one single place where you were recording that pointer, and now you have no way to access it. There's your memory leak. Okay, so how to avoid these terrible problems? The best practice here, the recommendation is don't have a function return a pointer to a newly created object. So we actually did this a couple times in our last semester programming, but it was at a point where we were just learning about pointers and we didn't have classes available to encapsulate this kind of activity. So there's a couple examples last semester where in practice you really want to avoid. Don't have a function that dynamically allocates an object and then returns a pointer, because the problem is whoever called it has to know about that and has to know that it's their responsibility to delete it and has to remember to actually delete it at the right time. And if the caller forgets to do that, takes the pointer, doesn't know that it's their responsibility to delete it, when that function goes away, you have these problems of just lost the pointer and now you have a memory leak. It's a very, once upon a time, maybe when you're working in C, there wasn't any other option. You had to have functions return pointers and you had to remember when to delete it. But if you're in that habit, it's so easy to overlook that. It's so easy to forget or misplace whose responsibility is. You really don't want to separate that stuff out. So the better idea, and this is really why C++ exists, and this is exactly why these aspects of classes exist, is exactly to avoid this terrible problem with pointers and dynamic memory allocation. So the better idea is just have one class who's responsible for creating and removing the dynamic memory allocation. And the idea is your constructor should allocate the object with new. The class has a private data member that's a pointer to keep track of that persistently as long as your object exists, okay, in all your accessors and mutators and whatever you need to do with it. And then the destructor is the place that deletes the object with the delete statement. And as you know, when you make an object, the constructor automatically runs, you can't avoid it. And when an object goes away, the destructor automatically runs, you can't avoid it. And now there's no possibility that you forget to run delete. It's going to happen no matter what. And this is why these things exist. Memory leaks and dynamic memory allocation problems, again, are the single biggest problem in programming. And 95% of program crashes and misbehavior and locking up systems and hacking vulnerabilities are entirely due to these kinds of pointer problems. So in some sense, you could say that C++ exists, classes exist, and constructor destructors are exactly for this purpose. So if you're working in C++, you ought to use those features the proper way. If you made a class that dynamically allocates new memory, it's your responsibility in the destructor to clean it up properly. Don't push that off to some other programmer that may possibly overlook it or miscommunicate it or forget about it. So here's an example of a class like that takes responsibility for the lifespan of a dynamically allocated object and avoids memory leaks. So here we have a class called goodMemory. It's sitting in a header file called goodmemory.h, of course. We are including some of those examples we saw before about the boxes in a video game here, in this case, Toy Box. So as you can see here, to manage the dynamic memory, you have a pointer being held as a private data member. So a toy box pointer, specifically toy boxes that just hold doubles for what it's worth, called SumBox pointer. And by making that private, nobody else can access it. Nobody can accidentally overwrite that pointer and lose access to the object. So that you do that. You have a constructor called goodMemory, and most of the time I would expect that in the constructor is where the new is, setting it up. And then you have a destructor called ~goodMemory, of course. And I would certainly expect that that's where the delete is going to be, that gets rid of the dynamically allocated memory. Notice that that is marked as virtual. And we said that in our prior interlude, that particularly with the destructors in a class hierarchy, it's really, really important to have a virtual destructor at the top of the class hierarchy chain, because when objects go away, they must call a destructor. So by setting that up, that's going to link with all the child children, and they'll know that there is a destructor for them to call. And then since it's virtual, they can also add more stuff to it if they need to. So that's actually a really important thing when you're making class hierarchies like that. And then there's some kind of method here, just for an example. And I think what that's going to do is take an item, and that's actually what's going to store it in the box that you're tracking in this class. So customarily, that's what happens. The constructor makes the new memory, the destructor deletes that memory, and then the whole time you're holding the pointer in a private data member that persists as long as this container object lives, and you don't accidentally have it in one function and then lose it when the function returns. So let's look at the implementation. So here's the implementation to those functions. This stuff's sitting in goodmemory.cpp. Now notice that this particular example is not a template class. It only uses toy boxes that hold doubles. It's not a template here. So because of that, we don't have to grapple with the whole, where do you put the code to a template class? Are you going to put it in a .hpp or a .tpp or something like that? That's not an issue. This here is just a normal standard non-template class, and yes, this goes in .cpp, and this gets compiled to its own object file. So a little bit simpler. Now, normally, I would expect to see a new in the constructor. That's not what's happening here. This constructor, since you haven't specified anything to save in it yet, just sets the SumBox pointer to null pointer. And again, that's the signal that you don't have any memory at that point yet. The destructor here, of course, calls delete to get rid of it at the end. But what they've got here, and this really ought to be the same name as on the prior slide, here's a method that's going to store something. You pass in the double that you want to store. Line 15 is where the new shows up. So you make a new toy box on the free store. You're storing that in the private member sumbox pointer. And then using that pointer, you can call the set item method and actually store this particular sum item, this double, in that object. And then it survives there, it persists. Sumbox, there's no way to overwrite sumbox pointer because it's a private data member, and that is handled and connected correctly until your good memory goes away. The destructor gets automatically called, and the delete cleanly cleans that up. No memory leak. So that's what that ought to look like. So usually at least 3 things: private data member, a constructor that usually sets it up, and a destructor that definitely cleans it up. So that's what normally controls the lifespan of a dynamically allocated object. That's good. Okay. Now, here, that's not the only pointer problem. As bad as memory leaks are, that's not the only problem. And again, this is something that I talk about in my second semester programming course. Is the other side of the problem is dangling pointers. So the memory leak problem is the object sitting on the free store, you lost the pointer. This problem is the opposite. You got the pointer, but you lost the thing in the free store. And this is called dangling pointers. So situations that can cause a dangling pointer is if you had an object, okay, and you deleted it, okay, but you forgot to set that member data to null pointer, and then some other piece of code sees the address, doesn't know that the delete happened, and tries to use that object that's sitting in the free store, but it's not there anymore. And then bam, buffer overflow, corrupting memory, some other objects getting corrupted, all kinds of things bad. The other thing is if you declare a pointer and forget to initialize it. Remember, when you make any local variable by default, including pointers, it starts off in C++ holding random garbage. So if you just declare a plain box pointer and don't do anything else with it, that is holding a random number, some random address in the memory system. And if you overlook the fact that it's an uninitialized pointer, you might try to arrow to it, but again, that's some garbage memory and you're just trashing memory in some terrible way. So the solution to that is definitely, when you make a new pointer, definitely immediately initialize it, either to using new or just hand it null pointer. Just make a new pointer and just immediately initialize it to null pointer as a signal that you don't have anything stored there yet. Okay, so example of a dangling pointer, you're in one of these situations where 2 parts of the code maybe had to reference this one object. You have an object on the free store, and we saw this before. You have one pointer called myBoxPointer, a second called yourBoxPointer. They're both referring to this one object in different parts of the code. That happens a lot, no problem with that. But, okay, you call delete. At some point you call delete using the myBoxPointer. And you even set it to null pointer. So you call delete myBoxPointer, and then you say myBoxPointer equals null pointer. You're doing everything you possibly can. But the problem is, in some other part of the code, your box pointer is still holding that address, and that other part of the code has no way of knowing that the delete happened. And at this point, there's no way to realize that you have an address in your box pointer, but there's no actual object on the free store in that location. So if you start doing your box pointer arrow something something, again, you're accessing corrupted memory, invalid memory, and you're doing all kinds of, you wind up getting undefined behavior of program crashes or other program crashes, or overwriting data or not, or randomly getting lucky or hacking vulnerabilities. And any horrible, terrible thing can possibly happen there. So to solve this version of a dangling pointer, we're going to need some new technology. And one solution to this is when we get up to C++ Interlude 4, we'll be presenting what's called smart pointers, or managed pointers, some people call them. And that will be a solution to tracking when things actually got deleted and not letting a second version of the pointer access that no longer existing object's memory. So that one we'll have to wait for, but there is a solution to this up in Interlude 4. Okay, let me just make a little side point here. So for what it's worth, I'm recording this video in February of 2025. And just coincidentally, these are the worst problems in computing. Okay, so issues around memory allocation and dangling pointers and memory leaks are just hands down. They're the biggest whale of a problem in all of computer science with all of software and all of technology. And as I've said before, anytime you talk about programs crashing or hacking vulnerabilities with systems, 95% of the time the problem is pointer problems, either dangling pointers or memory leaks. And we have been wrestling and struggling with this for years. Like I say, the existence of classes with constructors and destructors, that's basically trying to solve this, trying to give a mechanism to solve this problem. As I record this video today, February 2025, Bjarne Stroustrup, the gentleman who we can thank for inventing C++ that was released 40 years ago in 1985, and Mr. Stroustrup was working on it for most of a decade before that, before he released it. So we're now 40 years after the release of C++. Bjarne Stroustrup still today published a new paper on some new ideas for new technologies for avoiding dangling pointers and memory leaks. So 40 years on, and the inventor is still directly involved in trying to evolve and advance C++ with some new strategies that he's going to propose in an attempt to avoid the dangling pointers problem, which is the single biggest problem in all of computing. So maybe the new technology that's coming down the pipe, maybe that will finally solve these problems that we've been dealing with for 40 plus years at this point. It hasn't happened yet. I hope it'll solve the problem. Either way, there will continue to be legacy code that has been running for years and years that people will still need to know about this issue. As long as there's cybersecurity happening, people will have to know about this issue. So maybe, if you're watching this video at some far point in the future where all these problems have been solved and it's impossible to have these dangling pointer type problems anymore, hopefully this will give you an idea about why those two technologies got invented and the problems that we have been grappling with for half a century or more. And you'll at least understand the low-level issues that required the kinds of solutions that Mr. Stroustrup is still proposing and still developing today, 40 years on, which is kind of amazing. So thanks for him for trying to deal with this. Okay, so a couple other things before we get done with this particular video. So dynamic allocation, we were looking at one object at a time. Don't forget, you can also allocate a whole array. We did it a number of times in our prior semester. So you can statically allocate an array on the stack. So if you're in a function and you do, in this case, double my array, whatever your size is, that's making it on the stack. It works. If your array is really big, it won't fit, which will be a problem. So if you're making a really big array, you probably need to use the new operator to put it on the free store. And here's an example of that where you're making a double pointer called unarray, and you're newly allocating a double array of whatever your size is. And in this case, it's size 50, but you could make it size 1,000 or size 1,000,000 or size 500 million probably, depending on how much memory you have in your system. And then, maybe that's happening in the constructor to a class. And then on the flip side, don't forget that to properly deallocate an array, you have to use the square brackets on the other side. You have to write delete, empty square brackets, name of your pointer. And at least the first time that I present that to students almost always forget about the square brackets they need when they're deleting an array. So again, one of those little weird things about C++ that you're kind of likely to possibly forget. Now, knowing about that, here's an algorithm for doubling the size of an existing dynamically allocated array. And we've seen this in our prior semester. That might have been a test question. It's an exercise in the book. We also talked about this is how STL vectors work, for what it's worth, when you need to get an array to get bigger. So the algorithm, to review that algorithm, let's say you have a pointer called an array that you've declared on the free store as a dynamically allocated array. So first of all, make a new pointer. We're going to call it old array here. Get a copy of that address. Okay. And we're doing that to make sure you don't overwrite the address. Now, declare a new double array of twice the size, right? That's going to show up on the free store. Store that pointer in an array. Now, if we hadn't just made a copy on the first line, we would have just overwritten the address and have a memory leak. But fortunately, we made a copy, so that's not happening. Now, what you need is a for loop that goes through the whole existing array and copies it over to the new one. So however big the original array was, you're looking at old array number 0, number 1, number 2, and copying it over to what I would say the first half of the new array. Once you've finally done all that copy job, then you can, and here's where the delete shows up with the square brackets, you can delete that pointer that you stored in old array, and the original smaller array gets cleanly cleared out of the free store. And you have this same pointer you started with, an array, is holding the address of your new double-sized array. Now notice one little detail here is all the data get copied to the first half, and the second half of your array, of your new array, is uninitialized with a bunch of garbage data. But hopefully you'll be using that later right after this code for something reasonable. But don't forget the latter half we didn't initialize. So we've seen that before. I think that the book at this point goes through and adds this to the first the array bag class I think that they've developed. And when they initially developed the array bag, to keep it simple, they had like a fixed small array size. And by adding this little piece of code, you can make your array bag just add more and more stuff and more stuff and more stuff and just get bigger when it needs to in the appropriate place. Okay, so very common little thing we do. We've seen that at least twice in our prior semester. Here it is again. And you can think about adding that to your array implementations so that you don't run out of space in your container object. So that's kind of neat. So don't forget about that. And then finally, we're going to come back to that example that we've been working on in the first two interludes. So remember that we developed this class hierarchy for kinds of boxes in a video game. And at this point, we have a box interface class at the top that's abstract. It has pure virtual functions. You cannot initialize, you cannot instantiate one of those kinds of things. It's just sitting there to give the signatures for the functions in all the child classes so that they're compatible. From that, we made a child class called plainbox that adds some data and does its functions a certain way. And then we made a child class of that called toybox that does the same thing but has a color. And we made another child class from plainbox called magicbox that importantly overrides the set item to actually ignore it after the first thing gets stored in there. So it looks like you put a second thing in there and it turns into the first thing. So there's our class hierarchy to date. And again, this is just standard UML telling me, tell me about a magic box. Well, you're getting stuff from the plain box, and plain box got stuff from the box interface, and that is what you customarily depict it as in the unified modeling language. Okay, so what can you do with it now? Let's say that you need to write a function that does something with any of those boxes. So there's a common task you need to do, and what this particular example is going to do is it takes in some kind of box, could be any one of those three, and a string, and stores that string in the box, whether it's a plain box, toy box, or magic box. That's a pretty obvious common job. So the function should place the item in whatever kind of box you have by invoking the box's setItem method. Obviously, that's what it's for. So we're just talking about boxes that just store strings to make this example a little easier. Okay, so here's an attempt. Here's a function like that. So the function is called placeInBox. It takes 2 arguments. It takes a plain box with a string reference, so you can change it for what it's worth, called the box. And then it also, as a second argument, takes a string called the item, the thing you're going to put in that box. And obviously, there's just one line of code here. You call the box dot set item, and you pass in whatever the item is. Okay, so, if you remember, don't forget that a toy box counts as it's a kind of plain box. Same thing for magic box. A magic box is a plain box. It's a subset of those kinds of things. So when you call this function, in addition to passing in a plain box, you can also pass in a toy box or a magic box, and the function will accept that perfectly fine. And you're trying to call setItem on it. Now, if you are using the initial version of the classes that we developed in Interlude 1, there's actually going to be a problem with that. So let's say you try to use that placeInBox function in this way. You make 2 strings, for what it's worth. There's a special item, which talks about riches, treasure maybe. And there's a string called hammer item, which is a low value, not very interesting old hammer. And you're going to make 2 of these boxes. So you make a plain box for a string called myPlainBox, and you call that placeInBox. You handed off myPlainBox with a hammer item, so it stores hammer in it first. Okay, you call plainBox on myPlainBox with special item, so it stores special item second. And then when you call myPlainBox.getItem, you're going to see special item. You're going to see the second thing that it passed in that overrode the first thing. That's what you would expect. Okay, now you make a magic box called myMagicBox. Remember, magic boxes are supposed to do a trick whereby the second thing you put in it ignores, and you just get the first thing back. You call placeInBox with this and hammer item, so hammer goes in as the first thing. You call placeInBox and pass in special item with the second thing, and then you look in the magic box, what's in there? Special item. Well, that's a mistake. The whole point to the magic box is that the second thing you put in turns into the first thing. We wanted to get the first thing, hammer item. That's the whole point. That's the trick that magic box is supposed to do, and that failed here in this particular case. Again, we're using the very first versions we ever wrote back in Interlude 1. And if you are familiar with what you need to, what you really want inheritance to do for you, you may already know, hopefully you remember, what we forgot to do at this point. And what the problem is that the way we defined the placeInBox function, right, the compiler by default is going to see, well, that's a plain box, right? In comes a pointer or a reference to a plain box. So all I know about by default in C++ is I know about the plain box's setItem function, the one that just puts it in, no questions asked, no trickery. Just tell me about a thing, it goes in the box. So by default, the compiler sees this, and at compile time, it just locks in, I call the plain box version of setItem, and it doesn't know about the redefined version of setItem that we gave the magic box to do its trick. So to fix this problem, we need some way to communicate to the compiler, hey, you can't lock in that one version of setItem. You're going to have to track the different redefined versions in the different child classes while the program's running, figure out which version to run at runtime, and that is called, what our book here calls, late binding. So probably you could guess that was what the solution was. So what you're going to have to do is you have to tag the parent version of that function with virtual to tell the system to do the extra work, track the fact we have multiple different types of objects running around our system. We have multiple different redefined versions of that function, and you'll have to track in real time which one's coming into this function and call the correct redefined version of that method. So virtual methods, and we've already seen that a couple times, but the real reason we need that is that's the signal to the compiler to perform the late binding, or for what it's worth in our prior semester, we called that dynamic binding, is what we call that. The dynamic binding necessary for polymorphism. So that when we talk about polymorphism, this is it, is tagging functions with virtual so that when you pass them into a function like that, the system is doing the work to track which type is it really, which type of object am I really dealing with, and call the correct redefined function automatically. If you don't tag the function with virtual, it doesn't do that extra work, and it only pays attention to the actual literal type in the piece of code. So here we're going to revise the original plain box class for that. This part we're looking at right here, no different whatsoever. The only thing we're changing about the class is down here on line 22, when we initially made setItem, we didn't make it virtual. Here we're making it virtual, and now throughout the entire class hierarchy, the system will know to track and be on the lookout for redefined versions of that function. So now that setItem is virtual, just recompile your code, recompile everything we wrote before, basically, and now basically do that same kind of slice of code. You have special item and hammer item. You make a plain box here. Now, for what it's worth, the other thing they did here to modify this a little bit is instead of a reference variable in the function place in box, they've rewritten that to take a pointer instead. There's really no difference. As long as your function either has a pointer or a reference, references are really just pointers in disguise, so it works exactly the same way. Probably most of the time in our applications, we will be using dynamically allocated memory. You'll be storing those addresses in pointers. So this is kind of a more conventional, normal thing that we'll see in most of our examples. So make a new dynamically allocated plain box, store it in a pointer. Pass that pointer and hammer item into place in box. Okay, so put hammer item in the box. Secondly, put special item in the box. Then take a look at it, and there ought to be the second thing in that normal box, and sure enough, that actually works. Because place in box called the set item for this kind of thing, for the plain box, correctly. Now, if you make your second thing, your magic box dynamically allocated, great. Get the pointer, great. Pass it into place in box with hammer item for the first thing. Place it, call place in box with that, and special item for the second thing, and then take a look at it, and hey, it actually does the magic trick of you're seeing a hammer item. You're magically seeing the first thing that you put in the box because it did that little trick of just ignoring the second thing. So that proves that we successfully, correctly called the different redefined version of set item that's sitting in place in box for what it's worth. We called the redefined version of set item that's specific to magic box. We did not just statically call the one for place in box, and now we have polymorphism happening. Is that place in box function knows which version of set item to call. And it calls one version for a plain box, and it calls a second version for magic box. That's what we want. That's what, without virtual, that doesn't happen. Now, as you probably heard me say maybe in first semester, by default, right, C++, by default, C++ tries to do things as efficiently as possible, do as little work as possible. So no virtual, it does static binding, it only calls the parent class version because that is easy. You want it to do the extra work to do this tracking, you tag it with virtual, and now it does extra work. If you're doing this kind of stuff in Java, Java made the opposite decision. Java says, if you're redefining functions, you probably want dynamic binding. We'll just do that work for you automatically. If you don't want that to happen and you want static binding, then you've got to tag a function with final to say, don't allow any more polymorphism from this. So again, two different philosophies between C++ and Java, but in C++, you want the dynamic binding, you need to tell it to do the extra work with the virtual keyword, and that's what's there. So frequently we'll be doing this kind of stuff. And again, this interlude was really about stuff you need for pointers. So item number one that we were looking at is you need pointers, and you need to be careful about them when you're using dynamically allocated memory to get access to the majority of memory on your system that you might call the heap, or our book here calls the free store. And secondly, polymorphism like this only works if you're using a pointer. If you actually have like a concrete local object, none of this works. But if you have a pointer or a reference, then the polymorphism kicks in for the virtual functions, and the system does automatically correctly call the redefined version of all the functions in your class hierarchy. So in our data structures course, as we build out larger class hierarchies and we experiment with different ways of implementing different functions, this is a lot of what we're going to be looking at. Virtual functions in a class hierarchy, dynamically allocating our objects so that it encapsulates all the work, right? Avoids the memory leaks with the constructor and the destructor and stuff like that. And then we will be able to make individual dedicated functions for jobs, and we can send any one of those in. And the system just figures out which version we're working with. So there's some important, fundamental, foundational stuff for stuff that we'll be doing in C++ all semester long. Okay, so in the next Interlude 3, we'll actually be seeing something that's probably new for our curriculum at Kingsborough, actually, is we've been talking about what happens when there's an error. Can you cleanly handle errors? And in the past, sometimes we've been using error codes as like a return value, but you can't always do that. So the more sophisticated thing you can do is what's called an exception in modern programming languages like C++ or Java or something like that. And so that is a way that you can kind of conveniently pass a dedicated message from one part of the code to another part of the code that there was an error very crisply, and then possibly fix it or possibly put up an error message or something like that. So that's kind of an important new thing for us that we'll add next time in Interlude 3 about exceptions. So I hope you'll join me for that, and I'll see you then.